Hey guys, welcome back to day 28. Now we're going to do Bonding Workbook 2, continuing on from the last video. And we're going to keep doing the Lewis structures. We're going to talk about the electron pair arrangement, or geometry, the shape, hybridization, of the central atoms, all of them, the polarity of the molecule or ion, if it is, and if there's resonance or not. First up is I3, and it should be I3 minus. It's triiodide. So the electron count for I3 minus, we have 3 times 7 electrons plus the 1 electron, 22 total. How is I3 laid out? Well, a couple ways to try. Let's try a straight line. Bond 2, 4, 6, 8, 10, 12, 14, 16. 18, 20, 22. Is that valid? Well, let's look. The terminal I's have 2, 4, 6, 8, 2, 4, 6, 8, and a formal charge of 1, 2, 3, 4, 5, 6, 7. So the formal charge is 0. The central atom has 2, 4, 6, 8, 10 electrons, and a formal charge of -1. Well, since the overall charge is -1, somebody has to be -1, and it works. Let's see. So that central iodine, the electron pair geometry or arrangement, looks like it's trigonal bipyramidal. All right, we have 1, 2, 3, 4, 5 pairs. Shape, I have 2 bonding pairs, 3 lone pairs, so it's going to be linear. My hybridization, sp3d. Polar, not polar. Symmetrical and the same element. And of course, no other way to draw this, there's no resonance. N3 minus. It should be N3 minus. My negative signs are not on here. N3 minus. Electron count. 3 times 5 electrons plus 1 electron gives me 16 electrons. Well, let's try 3 N's in a row again. N, N, N. Minus. C, 2, 4, 6, 8, 10, 12, 14, 16. I have 16 electrons on, and in the middle only has 2, 4. So resonance, probably, because we have double bonds. Let's see. So if I erase 2 electrons from both sides and make double bonds, make double bonds from both sides. There we go. That works. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. I could have gone and 2, 4, 6, 8, 10, 12, 14, 16, or we could have done it as and that way. Either way, so we'll talk about that 1 second. First, the central atom, the electron pair geometry would be linear, 2 pairs. Shape is also going to be linear. Hybridization then is, of course, sp. Polar? Nope, not polar. And unequal resonance. So unequal resonance because the formal charge kind of moves. So there are 3 resonance structures here. The formal charge kind of moves and changes a little bit. So right now it would be -1, 0, and -1, where we have 0, negative, +1, and -2. So unequal resonance. COCl2, electron count. 4, plus 6 plus 2 times 7. So that's 24 electrons. How is it arranged? Well, carbon's probably in the middle. It's written first and the least electronegative. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Wonderful. Except carbon's not. So what do we do with carbon here? Well, I need a double bond. Do I double bond from chlorine or oxygen? And there is an answer here. And that answer happens to be oxygen. Why? Because if I double bond from oxygen, what's the formal charge of everything? 2, 4, 5, 6 has 6, 0, 0, 0, and 0. So before I double bond from oxygen, oxygen was -1. Minimize formal charge if possible. So there we go. The electron pair geometry of carbon, 3 pairs, trigonal, planar. Shape is also the same thing because there's no lone pairs. Hybridization, sp2. Polar, yes, because oxygen's top 5 and it's more electronegative than the chlorine, so it's not symmetrical. And I have to have the double bond there, and the double bond's not moving. I can't take the double bond away, so there is no resonance. Next one is xenon tetrafluoride. Electron count here. 8 electrons plus 4 times 7 electrons. So what's that? 36 electrons. Central atom's not fluorine, so F, X, E, F, F, F. Bond them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Well, that's 4 left over. 34, 36. Okay, let's go with it. Electron pair geometry. Why am I going with it? Well, because fluorine has 8 and xenon can have more than 8. So electron pair geometry would be octahedral. Shape. Well, we have 4 2 lone pairs. That's square. Planar. Hybridization. sp3d2. Is this polar? Not polar. Why is it not polar? Because those are 90-degree bond angles. It's symmetrical. And resonance? Nope, no resonance. Wonderful. S2O32 minus. Should be 2 minus there. Thiosulfate. And so let's do the electron count. 2 times 6 electrons plus 3 times 6 electrons. So that's 5 times 6. And then 2 more electrons. 32 electrons. How is this arranged? Well, one of the sulfurs is probably in the middle. Sulfur, oxygen. Well, I kind of want to come down the line. Hold on. Sulfur, oxygen. No. There we go. Got it. I'm with it now. 2 minus. Bond them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And you guys probably know that 32 times 4 is, or 32 divided by 4 is 8. 8 times 4 is 32. There we go. Electron pair geometry. Everything has 8, so EPG is tetrahedral. Your shape is also tetrahedral. Hybridization. sp3. Polar. Well, I have top 5s on the outside, but not everywhere, so yes, it is polar. Resonance. What do we think? Well, what's the formal charges? Sulfur is 1, 2, 3. Sulfur is plus 2. Can we minimize that? Well, this sulfur is 1, 2, 3, 4, 5, 6, 7, minus 1. If I double bond the sulfur here, now this sulfur 2, 4, 6, no formal charge, and that it's hard to tell the difference in that color. Let's try this color. No formal charge. 1, 2, 3, 4, 5. So sulfur still has a plus 1 formal charge. And 1, 2, 3, 4, 5, 6, 7, minus 1 for all the oxygens. So it doesn't matter which one I take from. I am going to take and draw a double bond with oxygen. Now this double bond, the blue one, can go all 3 oxygens. So it does resonance. So that has equivalent resonance structures. So it does have resonance. Sulfur is least electronegative, so that's why sulfur will always have the double bond. Now, if sulfur didn't have a double bond, and 2 oxygens did, it would be unequivalent resonance structure, but that's okay. Ozone. 3 times 6 electrons, 18 electrons. 3 oxygens, O, 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 bond them. 2, 4, 6, 8, 10, 12, 14, 16. Extra on the center is 18, but that's still not good. I need to make a double bond. Doesn't matter which side. No, I could have done that way. Or we could double bond this side. So there's equivalent resonance. In fact, this is one of the examples we did with equivalent resonance structures. So that electron pair geometry of the central oxygen would be 1, 2, 3 pairs bent. No, sorry, trigonal, the shape is bent. Trigonal planar. The shape is bent because there's a lone pair. Hybridization then is sp2. Is this polar? Slightly polar. More polarizable than polar, but slightly. And of course there is resonance. Propane. Saturated hydrocarbon. Valence electrons for propane, 3 times 4 electrons for carbon, plus 8 times 1 electron for hydrogen. That will give me 12 and 8, 20 electrons. And now this, I called it a hydro, H-Y-D-R-O, carbon. And the reason it's a hydrocarbon, it's just carbon and hydrogen. So how do these lay out? H, C, 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 H. There we are. Let's bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Electron pair geometry for all C's, all the carbons. The electron pair geometry will be tetrahedral. The shape, same thing. The hybridization is also sp3. Not polar. These are, by definition, not polar. And when they're all saturated, which means they're all single bonds, there's no double bonds, no lone pairs, there is no resonance. So sp3 carbons do not have resonance. That's good to know. One of our favorite compounds by what we spend, depending on your vehicle. There's a lot of people who like trucks and big SUVs, and octane is a major component of gasoline, and this is octane, and we spend quite a bit of money on it sometimes. And some of you guys do not spend hardly any money on octane. You got little tiny cars that get really good gas mileage, or hybrid cars or whatnot. And some of you guys have cars that get like 12, 14 miles an gallon. So it just depends. But octane, what do you think here? We have electrons, 8 times 4 electrons plus 18 times 1 electron. And that would look like it will have how many? 32 plus 18, was that 50 electrons? So how is it arranged? Now, these are getting so big that it doesn't really matter, but H1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now this is not the octane and gasoline, it's mostly isooctane. And so since it's isooctane, what that means is, let's say you take these 3 carbons off, take the last 3 carbons off, so you break this bond, like take this hydrogen, put it there, and all these guys where that hydrogen is. So it's in the middle. Or you can put it in, you can use that hydrogen if you want. It doesn't really matter where you're going to put it. It's just not straight line. But I digress. And so the answers are the same up there. So all C's, all the carbons are the same up there. All saturated hydrocarbons. All nonpolar, no resonance. There you go. Number 9. POCl3. Well, let's look at the electrons for this one. 5 electrons plus 6 electrons plus 3 times 7 electrons. 21, that's an 11 is 32 electrons. Central atom. Looks like it's P. P, O, Cl, Cl, Cl. Bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. You guys, 8 times 4 is 32. And so we'll get everything here like this. 8 times 4, 32. There's 32. We're good. The best Lewis structure, well, house formal charge. Chlorine has 7, brought in 7, good. Phosphorus has 4, brought in 5, plus 1. Oxygen, ooh, minus 1. Can I minimize it? Yes, because phosphorus can violate the octet rule. Wonderful news. Now, electron pair geometry will be still tetrahedral. Even though there's a double bond, it still counts as 1. That means the shape is also tetrahedral. Hybridization, sp3. Polar, yes, it's slightly polar because it's not symmetrical. And resonance, we have unequivalent resonance because we're moving formal charge. Number 10, number 11, try these. You're going to draw the Lewis structure for benzene, and it has 30 electrons. Try to draw the Lewis structure of benzene with 30 electrons. So that's 6 times 4 electrons. Try to draw it. Go ahead and hit pause. Try to draw it. Try to figure it out. Don't just Google it because that does nothing for you. But just draw the correct Lewis structure of benzene and see what you get. You get something like this. It's close. That's close. Something like this is really close, but the problem is there's missing a bond right here, and I have a lone pair right there. So think about the chances of you closing this up. All right, let's try arranging it in a hexagon. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then it doesn't matter where, 26, 28, 30. There's your 30 electrons, and there's your Lewis structure. Technically speaking, these double bonds go to everybody, so a lot of times you'll just see a dotted line or a circle in the middle for benzene. They're all trigonal planar. Geometry and shape, it's all sp2 hybridized carbon, so that's why there's resonance. It's nonpolar. Let's look at pyridine now. Try to come up with pyridine. If you notice, it's the same valence electron, so 5 times 4 electrons plus 5 times 1 electron plus 5 electrons. Still 30 electrons. Let's go ahead and pause. Try to draw Lewis structure of pyridine, knowing what we just did for benzene. All right, so what are we doing here? Hopefully you have on the page an N and the C's in a hexagon with the H's. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, lone pair on nitrogen, 30. And there's pyridine. sp2, even the nitrogen's sp2. The nitrogen's just bent. It's not trigonal planar, but it's still a trigonal planar electron pair geometry. The last one, naphthalene. Draw both. There's actually 3 resonance structures of naphthalene. C10H8. So we have 10 times 4 electrons plus 8 times 1 electron. So that's 48 electrons. And I'll just draw one of the Lewis structures, one of the resonance structures, but there's 3 of them. So if I have carbon, we just did this. So chances are this is something. Now, I've had students in class do a 10-membered ring. The problem with the 10-membered ring is that it doesn't work out for the geometry of the angles. Right? Trigonal planar has a 120-degree bond angle. The inside of a hexagon is 120-degree angles. So it matches very well. So knowing our bond angles kind of helps us say, is this a reasonable Lewis structure? I might be able to put enough lines on the paper, but that doesn't mean that the Lewis structure looks anything like it, because we just can't get it done that way. So this would be 2, 4, 6, 8, 10, 12. I have 4 more hydrogens. Or, sorry, I have 8 more hydrogens. I have 4 more carbons. So 1, 2, 3, 4. 2, 2, 2, 2, 2. So I have 2 hexagons there, don't we? Now we put hydrogens around the carbons that are not connected to both sides of the hexagon. Let's see. 2, 2. I'm using colors to coordinate here. Oh no, it moved on me. There, 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 and there. So electron count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. 40, 42, 44, 46, 48. And how you put those orange lines on is how the double bonds move. You move them. You just rotate them, start in a different spot, and draw another one. So what do I mean by that? So that's one Lewis structure. There was none here, so there, there, there. And then that's good, there, and there. That's one of them. That's another one, because there's 5 double bonds. And then the other one I didn't draw had a double bond here. There, there, and there, there, and there. That's it. Those are your 3 Lewis structures for naphthalene. So that concludes all the Lewis structures I'm going to do with you. That concludes all the bonding theories, all the shapes, polarity, everything. Feel free to reach out to me if you have any questions. Hopefully confident, and we will talk to you guys later. Take care.